Always.
But this one is works.
Yeah, yeah. I don't like this. You have to switch between.
Hey, how's it going? I'm alive. Yeah, we've met a couple of times before.
Well, yeah, I don't know.
You don't know.
Maybe 5 or 6. There's one there with German.
My son's name is Elias.
Oh, really? Okay.
Okay.
Oh, I didn't know that.
Danny.
I went to McGill and then I went to Quran. So it's sort of yeah.
Are you Canadian?
I grew up in Toronto. Yeah.
Oh, I didn't know.
Yeah. I'm a dual citizen. My parents are American, but I grew up here.
Yeah. Should be like times.
Did they tell you it was okay to go to Quran?
They have a very good vibe.
My parents?
No,
What?
I didn't go.
They encouraged me.
I was
Yeah.
ushered into the chairman's office. With my sis. He said, that is not a mathematics department.
Oh, really? Like you shouldn't go. That's crazy. Wait, this was in the 90s?
I'm a bit older than this. That was in 1985.
Okay. Oh, I don't know why I thought. I don't know. I've looked at what?
They were angry that I went to visit.
Really? So Rustam encouraged me to go.
Yeah.
He said, "You gotta go to Quran. You gotta go to Quran." Right. Oh, wait, but isn't that's like really? I don't know. Isn't that's like post the golden era? Is that right? I don't know. Really? I mean, I don't know.
I'm not joking.
But like how? What do you mean? Wasn't it always like super strong analysis and
McGill was at a category.
okay, I see. So that wasn't even math, I guess. I see. Oh, should I start or oh I need my slides.
Oh, you want slides?
Yeah.
Sorry, did you call that guy?
emailed.
I could try to do it by hand, but I'm not sure.
Such a good thing. It's gonna be.
Unprepared board talk. I'm not sure.
We just thought we should get some hand-drawn pictures.
Okay, I don't want to run late.
Sorry, that's our fault. We'll fix it.
I can start. I mean, I can do the first slide for sure. But okay.
That's right.
Well, I guess Toronto in the 80s would have been, New York is a different town. Right? That is,
great.
yeah. There's a security guard, and he was the security guard for Toronto for like 40 years, I think. He just retired just recently. You probably knew him when. Like a big bald guy. I'm forgetting his name. But
Yeah, but there was one main guy when I was there, and he retired.
oh, okay. I don't, maybe it was his.
No, there was that guy was the young guy.
The young guy, right? For me, he was the old guy. Anyway, he would tell stories about New York in the 80s. And,
Yeah.
I remember the late 80s.
The what?
The late 80s.
The late 80s.
Yeah.
In New York.
Yeah, I mean, we went to visit some grad student and we lived there for a year in maybe nobody was.
This one?
Yeah, that's it. And the Zoom is on. Is that right?
Decade away.
Okay.
Early 90s.
And is there a clicker? Okay, great. Sorry about that, everyone.
It's helpful.
Oh, I'm sorry. I guess you were waiting for me. Thanks. Bye.
previous slide. All of this.
How does the pointer work?
Hold it.
Oh, oh, it's kind of weird. Okay. Okay, great.
All right, thank you everyone for coming. This is our last seminar of the semester. And today we have Elias Hess-Childs from Carnegie Mellon, who will tell us about large deviation principles for singular Riesz-type diffusive flows.
Okay, thank you very much. Thank you for the invite. I'm very happy to come up. I grew up in Toronto, so it's always good to come home. Yeah, so today I'm going to be talking about sort of a specific class of statistical physical model. In particular, I'm going to be talking about how sort of some recent innovations for proving these systems satisfy mean field convergence can be combined with sort of a pretty well-known argument for proving interacting particle systems satisfy LDPs to imply the specific model satisfies LDPs. So first, this is sort of the general model I'm interested in. I call it a mean field interacting diffusion. It's a system of n particles in RD or TD, where TD is the flat torus, governed by this SDE. So each particle, there we go, interacts with every other particle via some kernel K, and that interaction is a mean field interaction. So it's the same interaction between every two particles, and there's a 1 over n in front of the sum. And then there's also some noise. And pretty much throughout the talk, I'll be assuming that WIT is our IID Wiener processes, and also that there's a positive fixed diffusion parameter. So, sometimes people are interested in sigma, depending on n, maybe going to 0 as n goes to infinity, but I'm just going to take it to be fixed. I'm also always going to take the initial conditions to be deterministic. So this is the system, a bunch of,
You call this mean field?
Mean field, yeah. That's the 1 over n sum. I mean, they all interact with each other in the same way.
Yeah, but it depends on their spatial location.
Yeah, sure. But it's the same, kernel.
Doesn't depend on n.
Sorry?
K doesn't depend on n.
Yeah, K doesn't depend on this. Yeah. Yeah, I didn't make this up. I mean, they're called, that's what they're called. Anyway, okay.
It would be like TSEP would be the mean field model.
Because that's just understand.
Yeah, but you just
So like if you think about I don't know how to.
K where nearest neighbors is something. And
I mean, if you think about every particle interacts with every other particle in the same way, so it's mean field, right? There's not. Anyway, okay, I'll continue.
You say you can't formulate this like this?
No, well, there's some implicit assumption here, because you're going to have a lot of particles. So there's, see, the distance to the distance
And
on
K doesn't depend on
Mellon.
K doesn't depend on
TSEP, the interaction would have to be distance 1 over n.
Yeah.
Yeah, like so. For example, if you take any two particles as n goes to infinity, they don't interact with each other, right? Interaction goes to 0.
Okay.
Right. Yeah, which is sort of the point actually of the model. Yeah. Okay, so the aggregate behavior or the macroscopic behavior is described by the empirical measure mu(n)t at some time t. This is a random element of the space of probability measures. I'm also interested in not just the macroscopic behavior at a fixed time, but also the evolution of macroscopic behavior. So for a fixed time horizon t, I'll often consider what I call the empirical trajectory. So this is a random function, random element of the space of functions from time to probability measures. Okay, so this is the system. Why do I care about the system? It has a pretty long history. I mean, this kind of system started popping up in the 50s and 60s by people like Dyson and McKean, and they were, to them, it was sort of a toy model of a gas. I'm sure there's,
Mark Cox,
and
he introduced.
are you sure about that?
It's called the Cox.
Well, I mean, is it called the? No, I'm not sure. McKean. I mean, people call them McKean-Vlasov. I don't know. There's the book. There's Katz's book where he introduced propagation of chaos, and he doesn't introduce this model in it. So maybe maybe I'm wrong. Sorry. Okay. Sure, Katz too. Yeah. Okay. So that's sort of the origins. Is in statistical physics. and you can show me. I mean, I was trying to find the earliest example. Recently, I went to a talk and the speaker asked all of us in the room, who came up with the Fokker-Planck equation? Who was it? Who first came up with it? And Einstein, I think there's a previous student, sorry, there's a student before Einstein actually who wrote it in like their thesis, but I didn't know this, but I don't know. I mean, I'm sure someone introduced it earlier too, right? Okay, anyway, so originally statistical physics model, 8 minutes already, okay, but since then they've kind of escaped. They show up all over the place. People use them as models of like economic agents or aggregation phenomena, or even for like the scaling limits of large neural networks. I'm just going to introduce a couple of my favorite examples if you're in 3D. And the interaction is a repulsive Coulomb interaction. This is a model of overdamped plasma or a Coulomb gas. If you're in 1D and you have this inverse power repulsion, and you let the diffusion parameter scale with n in this way, this is Dyson Brownian motion. So it's the law of the eigenvalues of Hermitian Brownian motion. If you're in 2D and you have a conservative inverse power interaction, this is a model of vortices in a viscous fluid. So every particle is a vortex, and then the diffusion is the viscosity of the fluid. And finally, there's a well-known model of the aggregation phenomena of bacteria, or chemotaxis, which is in 2 dimensions, and then this interaction is repulsive inverse power law. Okay, so these are some, sort of nice examples. All of these examples have singular Riesz-type interactions. So the interaction kernel is given by some matrix multiplied by the gradient of G, where G is Riesz potential, right? And in particular, just to remind you, G solves this equation, right? So it's indexed by parameter, some parameter S, and it solves this equation. So I'm going to say a mean field interacting diffusion with repulsive or conservative Riesz-type interactions. So if this matrix M is negative semi-definite, I'm going to call it a Riesz-type diffusive flow. Yeah. Yes. So here's the model. I'm sort of generally interested in these interacting particles models, mean field interacting particle models, specifically maybe in one-third Riesz interactions. What do I actually want to show they satisfy? What kind of analysis do I want to do? What kind of limit theorems do I want to show they hold? Well, McKean, when he studied them, he studied them as systems that satisfy something called mean field convergence. So he was interested in sort of connecting molecular models to effective equations. He saw these as a molecular model of a gas, and he was interested in showing that as n goes to infinity, as the number of particles goes to infinity, this converges to a PDE, a determinist PDE. And that's exactly what mean field convergence is. So we say a system satisfies mean field convergence if the empirical measures of the initial conditions, if it converges, if this implies, as the number of particles goes to infinity, that the empirical measure at a future time converges to mu t, where mu t is the solution to the McKean-Vlasov equation with this nice parabolic, nonlinear parabolic PDE. And this is deterministic, right? So this is mean field convergence. One way to think about it is it's a law of large numbers for these systems, right? So the number of particles goes to infinity. These empirical measures, which are random, concentrate on some deterministic object, namely the McKean-Vlasov equation. Yeah, so it justifies the McKean-Vlasov equation as the continuum equation for these systems. There's a pretty simple formal argument that shows that you should expect this for these systems, but it can be quite hard to actually rigorously justify, especially when the interaction is singular, like Riesz-type. Okay, so that's the first thing. This is the typical behavior of these systems as n goes to infinity. I'm also interested in their atypical behavior. So if nu is some measured trajectory and it's not the solution to the McKean-Vlasov equation, you expect that the probability mu n is near nu goes to 0, as n goes to infinity, right? But I'm also actually interested in the exponential rate of decay of this probability. In particular, I want to find some function I. So this probability decays like e to the minus ni nu. And of course, what I want is an LDP. I mean, this is an LDP, right? So just to remind you, mu n satisfy an LDP with good rate function I from the space of measured trajectories if I has compact sublevel sets you get this upper bound for any closed set, and you get this lower bound for any open set, right? An LDP. So these are the two things I'm interested in proving. When K is regular, so say continuous or bounded Lipschitz, or maybe just locally Lipschitz, these problems have been thoroughly investigated, going back to McKean's work for the mean field convergence, and also Dawson and Gartner for large deviation principles. And in particular, there's a pretty interesting paper that came out pretty recently in 2020 by Kogi, Duschel, Fritz, and Morelli, where they sort of introduced a global framework for proving limit theorems for these systems when the interaction is regular. It's a bounded Lipschitz. So what they showed that in that case, you can construct a continuous function from the space of probability measures on trajectories to the space of probability measures on trajectories, so that this function maps the empirical measure of the noise to the empirical measure of the interacting process. And this is somehow a pretty simple argument. Once you have the idea to do it, it's sort of a Picard iteration in infinite dimensions. And once you do this, if your noise satisfies, a law of large numbers, then immediately your interacting process does as well. Or the same for an LDP, right? If the noise satisfies an LDP, you can just use the contraction principle, and immediately the interacting process does. So the setting when the interaction is regular, you can really, all you have to do is understand the noise and the asymptotic behavior of the noise, and you can immediately just lift that to the asymptotic behavior of the interacting process. They also show you can prove CLTs doing this, right? And it's sort of a nice, I think the paper is called McKean-Vlasov, pathwise McKean-Vlasov theory. So it has a very, general title.
This is just abstract, right? The fee isn't explicit.
No, it's explicit. Yeah, it's explicit. Yeah. Oh, I don't know. Yeah, it's a really nice paper. Yeah. No, it's explicit. Yeah, it's explicit. Okay. Yeah. Okay, I guess it depends what you mean by explicit.
We
Yeah.
have a disagreement.
Yeah, so I don't know. I don't want to get in the middle of it. Oh yeah, for sure. Yeah, should be. Yeah, it's a
Like an explicit.
essentially, the point is you should think of something like Friedland-Wenzel theory. So if you have an additive SDE, you can map the noise to the solution of the ODE, right? SDE additive noise is really an ODE, and that's a continuous map. And that's essentially what they show, but they're doing it on the level of measures. Yeah. So it's really just a Picard argument. That's why you really need K to be bounded Lipschitz. Yeah. I actually, Gerard Benarus told me I should try to do something like this. And then I tried and I did it. And I was super happy. And then I found this paper and I was heartbroken. So I know. And I looked in the paper and they used the same notation I used when I wrote up the argument. So yeah, I like this paper quite a bit. I think it's a nice paper. But anyway, and not just because I accidentally discovered it on my own. Okay, so one thing is this sort of strategy, it's just never going to work when the interaction is singular, right? And I say that because, unless you have some really strong topology on your noise, when you have a singularity, small perturbations are going to cause bad things to happen, right? You have singularity, move something a little bit, totally different behavior can happen. So this is just this isn't the right approach when K.
In what sense are you saying this? Is there any example of a theorem that shows that this is the case, or
no?
or is
It's just
never been done?
it's never been done. Yeah, you can see if you try to do this proof, it really won't. Okay, one thing is here, you don't need the noise to be a diffusion or anything, right? For this, you can have the noise be anything you want, right? And you're not using any kind of regularization or anything. And even to discuss the existence of the SDE system, when you have a singularity, you're going to have to use regularizations of the noise, right? So somehow a different regime, right?
It could be somehow that the noise converges so strongly that it cancels out the singularity. problem? No,
Yeah, but then you'd have to analyze the noise, right? I mean, I don't know.
It's also true that hardly anybody sees the singularity.
Yeah, that's true. Yeah. I mean, I tried to get, I thought about it a while. I mean, I don't know. Like you can try to do something like you can try and bound how close particles get, right? And then you're like away from that set, your interaction is basically, regular or something. But you can't bound those probabilities well enough. Like, I don't know, at least for the LDP, right? Mean field limit is different. Okay. So, I mean, it's not a theorem, right? But, I mean, it's my perspective. And actually, in the literature, often when you have a bounded singularity, you really have to do something special. You have to do something like look at some notion of distance, which is paired to that singularity. Okay. And for example, it's only relatively recently, like in the last 6 years, that Riesz-type flows, these systems with Riesz-type interactions have been shown to satisfy mean-field convergence in sort of full generality. So there's, you can see there are kind of a couple groups who've been working on this. And really, the big breakthrough was this paper in 2020 by my PhD supervisor, Sylvia Surfati, where she introduced an interaction-dependent distance called the modulated energy. And somehow this is the right distance to talk about mean field convergence, to talk about the convergence of the empirical measure to the limiting equation n. So this is the definition. You define it between some particle configuration and measure mu, and it's equal to this integral against that Riesz potential, where you have a tensor of the difference between the empirical measure and mu. So here, mu n is the empirical measure associated to that point configuration. And here, because G has a singularity and mu n has Dirac's, you have to exclude the diagonal, or else this thing is infinity.
I forgot what G is.
The Riesz potential. Should I write it on the board? Yeah, I'll write it. Or
In terms of K, it's the
K is equal to something like minus grad G. So here they're repelling each other, right? In this setting. So think of electrostatic interaction, right? And actually, if you think about electrostatic interaction, what this is it's the electric energy between a bunch of point charges and an oppositely charged continuum of charges. Another way to think about it is it's a renormalized version of a negative Sobolev norm, right? So if you think of this PDE that G solves, right? If you integrate by parts, you could add back the diagonal and you would find this is the case. Of course, this is infinity because mu n doesn't live in this negative Sobolev space. Yeah. So in particular, if you have a sequence of trajectories and the modulated energy converges to 0 for that sequence. Sorry, sequence of point configurations. What?
Is that because of the diagonal? That the right hand side is infinity and the left hand side is nothing?
Yeah, exactly. Yeah, this has a singularity. So when the Dirac in the empirical measure hits itself, right, you get G of 0, which is infinity. Yeah. So you have to all you're doing is taking those out, those self interactions out, essentially, right? But morally, it's equal to this. Yeah. Okay, but in particular, if fn, xn, mu goes to 0 and then goes to infinity, then mu n has to converge to mu. Right. So it controls reconvergence. Actually converges, it controls convergence in certain negative Sobolev spaces. But okay. It's also it's not positive, right? But it's asymptotically positive. Then goes to infinity, it becomes positive. So it's almost like a distance. Not quite like a distance. Okay, how do you show mean field convergence using it? You show a Grunwald inequality. So you look at the modulated energy between the Riesz flow and the limit, the mean field limit, and you do something like you take Ito's formula, or something. You take a time derivative of it, and some term shows up that looks like this, and then you prove an inequality, and that lets you So you prove that the term that shows up when you take the apply Ito's formula to the modulated energy is bounded by the modulated energy again, right? And that lets you show mean field convergence essentially. In particular, when S is less than d minus 2, you can show something like the expectation, the modulated energy at time t is bounded by the expectation of the modulated energy at time 0 plus some error that disappears. Okay, and this is really this was the key piece of the puzzle. Was this inequality? It's not that easy to show. It's called a commutator estimate. But I don't know. Does that make sense? Yeah, that's what you do. I mean, it's sort of standard. You want to prove a Cronwall inequality and take a time derivative, use a bound. So that's how they do it essentially. Okay. What about large deviation principles for these systems? Well, there are relatively few regimes where they've been proven. So in particular, they've been proven in sort of the Dyson-Brownian motion regime in the early 2000s. And recently there was a paper that proved them in the I'm having a hard time with the laser pointer, with the vortices in a viscous fluid case. But that's pretty much it, actually. These are the only known results I know for proving these systems satisfy LDPs. And in particular, in all of these examples, S is equal to 0 and the dimension is less or equal than 2. And all of them somehow critically use that in their proofs. Okay, so there's already a question, what goes wrong when S is greater than 0, and can you fix it, right? They also, they all use sort of the same general strategy to prove the LDP, which was introduced by Kipnis and Ola in the late 80s to study the large deviations of sort of a whole bunch of families of interacting particle systems, in particular things like exclusion processes. And I think of this strategy to prove LDPs as sort of like Cramer's theorem. It has a lot of analogies to Cramer's theorem. You prove three things. First, you prove exponential tightness, right? So this is somehow proving tightness in the large deviations regime, and this lets you reduce the proving large deviation principle to proving a local large deviation principle, so local estimate. You prove a local upper bound, so something like this. And this
Why is that?
what?
Why does the exponential tightness reduce it to local?
So what it lets you do is it lets you you only have to prove the LDP upper bound on compact sets, and then what you can do is you can cover a compact set with a bunch of little balls, and you prove the LDP on all the balls, and you like stitch it all together. Essentially, does that make sense? And the lower bound you don't need the exponential tightness. Yeah, somehow it's like you want to prove something on only on compact sets, so you only have to prove it on balls. So you prove some tightness of your sequence of measures. Yeah, it's pretty standard idea that's used in LDP theory. Yeah. You prove a local upper bound. This requires Chebyshev's. It's just like a Chebyshev inequality plus martingale bound. And then for the lower bound, you combine a mean filled limit with a tilting argument to get a lower bound. And if you go and look in Dembo and Zaituni's book on large deviation principles, this is almost exactly how the proof of Cramer's theorem goes. Upper bound is Chebyshev's, lower bound is a tilting argument with a law of large numbers. Of course, here our law of large numbers is going to be a mean filled limit.
Even in Duret.
What?
Even in Duret, this is how it's.
Oh, sure. Yeah. Actually, I don't know. I mean, is there a better proof of Cramer's theorem? I don't know. Yeah. Okay. So I'm going to go over the argument because it matters, for my purposes. But I'm just going to do it in a simple case, which is the non-interacting setting. So if you just have, a bunch of, noise, you have no interaction. And this is actually what they prove in the Kipnis-Ola paper. Slightly different regime, but this is essentially what they prove. And they show that if the initial empirical measure converges to some mu naught, then mu n satisfy an LDP in this space with this variational rate function. In particular, it's a supremum over some function s nu phi, where phi is in some space of sufficiently continuous functions, and the rate function has this form. So here, there are two parts to it. There's a linear term in phi, and then a quadratic term in phi. And if you just look at the linear term, this is sort of, this would give you the definition of a weak solution to the diffusion equation. That is, if this term is 0 for all phi for some measure nu has to be a weak solution. I mean, to the diffusion equation, heat equation, right? Okay. In particular, this function is continuous with respect to this topological space. Okay. I'm not going to talk about how you prove exponential tightness. I'm just going to talk about how you prove the upper bound. So to prove the upper bound, what you do is you test phi, some test function, against your empirical measure, and then you use Ito's formula, and you find this equation. So immediately, this is starting to look like this function S nu phi, right? It has this, this corresponds to diffusion, and then there's a martingale at the end, right? Okay. This is just an equation. The last term is a martingale. And what this means is, if you rearrange this equation, what you find is n times this function, S mu and phi, is equal to a martingale minus the quadratic variation of a martingale. Okay. And what you like about this is that this term on the right, the exponential of it is a martingale too, right? In particular, it has constant expectation. Okay. So then once you have this, you can just apply Chebyshev's inequality. You can bound the probability that mu and its symbol by here, we're just rewriting 1. And then with Chebyshev's, you find this. And so here there's an infimum over rho in the ball of this function. And this expectation is just equal to 1. So the thing is a martingale. And you find this bound. And since this function is continuous, this immediately gives you your local upper bound, essentially.
There's a school calls Markov's inequality Chebyshev, right? This you're part of the school.
Yeah, I call everything Chebyshev inequality.
I call everything.
This is what people call Markov. Right?
I mean, I call it exponent. I call it Chebyshev. There's one inequality, right? I don't know.
Is there a reason?
Because it's variant and Poldus is called Chebyshev.
I see.
Sorry.
Chebyshev's the variance.
Yeah, exactly. That's right.
This
I
is
think
this is the meme.
when Ofer, when I learned LDPs from Ofer, I think he called it Chebyshev's inequality. Yeah. I remember going to a graduate stats class, and they showed 5 different names for Chebyshev's inequality, and being like, "This is way too much to remember. I'm never going to do it." Okay, I'll continue. Sorry. So you can conclude the local upper bound by taking a supremum over this function. For the lower bound, you only have to prove the lower bound when the rate function is finite, right? And you can actually use the form of it to show if the rate function is finite, then nu actually has to solve a perturbation of the mean field limit for the system. In particular, nu has to solve, it has to be a weak solution to this equation. So it's just a heat equation, but now there's an added drift. And this drift is related to the rate function by this equation. Okay. So this follows by a pretty simple argument using the fact that this rate function was a supremum over a linear term minus a quadratic term. And if you kind of use Riesz representation, you can show this. So this is pretty interesting. It says somehow that the only measured trajectories that matter in the LDP, they look like perturbations of the limiting equation for this system. They're the same, but they have an additional drift. And more so, if V is sufficiently regular, you actually know that the empirical measure associated to this system should converge to nu, right? If you look at the empirical measure of this system, just by the law of large numbers, it should converge to this equation, right?
So I don't even know what you're talking about. So is this, this is incomprehensible to anyone but the experts. You're just going too fast. So
I'm sorry.
Are you talking about the general non-interacting one, or are you talking about?
Yeah, non-interacting.
So
We're still.
it's not even your model yet. Right?
No. Yeah.
Okay.
Yeah.
That's good. At least I got that much.
Okay, all I'm saying is if the rate function is finite, then for some measured trajectory, then that measured trajectory has to solve an equation. Okay, and not just that, the equation it's a drift diffusion equation, right? Right. Of course, the original thing was just a diffusion, so it's mean field limit or it's law of large numbers. It's just a diffusion, right? So this looks like a perturbation of that system, right? Yeah, And actually, the rate function is also related to the size of that perturbation. Does that make sense? I mean, it's just an argument to do it. I don't know. I don't know.
He wants to tilt.
Yeah.
And so this is how it's.
I believe it. I believe it's just too much stuff. This is why it's good to have maybe board topics. I wrote a paper, on this kind of stuff.
I'm sorry.
It's okay. I'm trying.
Yeah.
It looks beautiful also.
So to continue,
Keep going, sorry.
Um,
Keep going.
so if B is regular enough that you can say make sense of this SDE, the empirical measure associated it should converge to this PDE. Okay, and not just that. Using the Gersonov theorem, you also understand. So here there's a PB to mean that the empirical measure here corresponds to the original system with this added drift. And if you look at the Gersonov theorem, lets you. I don't know what's going on. Gersonov theorem lets you show something like this. It lets you show that the rate-on-Nicotin derivative between the original system and the perturbed system looks like something like e to the minus n to the rate function when the empirical measure is near this new. Okay, and then you can just conclude the lower bound using the Jensen's inequality of the law of large numbers. Okay, a little quick, admittedly, but that's how you do it. I mean, you show the paths that are relevant to the LDP. They solve a perturbation of the system, and then you you tilt and use a law of large numbers. And it gives you the result. Of course, here I had some regularity requirement of B. So if nu and B are not that regular, you have to construct regularization, nu k and bk, so that nu k converges to nu and the rate function converges as well. And that lets you recover the lower bound for arbitrary measure trajectories. Okay, so there's a sketch, quick sketch. What happens when you add a singular drift? How does this sketch change? Well, so if we add this new term here, a new drift, when you do this Ito's formula computation, you get a new term, right? Which looks like this. And this really just comes from this interaction here, right? Okay, you just get a new term from the drift. So that gives you a natural modification to the previous function, s nu phi. In particular, you add a new term here. Okay. The issue is this function is not continuous in this topology, right? So in the upper bound, we really needed continuity. In fact, this isn't even well defined necessarily for arbitrary measured trajectories, right? Because you have a singularity. So that's bad.
So for example, if you had those models where you had the nice case,
This would be continuous immediately.
then you could actually use the same method.
Yeah. This would immediately be continuous, exactly. Yeah. But here it's not. I mean, it's not even well
It's
defined.
bad,
Yeah, it's bad. Okay. Also, if you continue to proceed formally for the lower bound, instead of getting these perturbed diffusion equations, you get perturbed Minkine-Vlasov equation. Right. So this is the Minkine-Vlasov equation, but now you have an additional drift. And now instead of just a law of large numbers, you really have to prove a mean field limit for these perturbed systems. Right. Exactly the same. Okay. Finally, when you try to recover this regularization argument, the nonlinearity in this equation causes problems. It just makes it much harder to do. VT, totally unexplicit. I mean, for a particular nu, you mean? Yeah, I mean, if I nu is less than infinity, then nu has to solve this equation essentially for some VT, and that VT has to have some integrability with respect to nu.
Is it even clear it's unique?
No, it's not
Is
even
it
clear it's
true?
unique. No, not in general.
Oh.
Yeah, I mean that's why you need the regularity,
Yeah.
because if you want the mean field limit, you need uniqueness, right? In the right regularity class, at least. Yeah. Okay, so a bunch of issues. How do you get around them? Well, you can use the modulated energy and the associated commutator estimate that were used to prove mean field convergence for these systems. So here's my first result. If S is in 0 to d minus 2, and you have repulsive interactions, you can show this. So you can show a local LDP for this system. So if the modulated energy of the initial convergence conditions converges to 0, then for any L infinity time, L infinity space path, you get a local LDP bound, but using the distance, the modulated energy, to talk about the distance between your point trajectories and the measured trajectory. Okay, and here S nu phi is exactly this equation. I mean, it's exactly this function before. So you can show this. Maybe this isn't that surprising. What I'm doing is I said this function wasn't continuous in this weak topology, but somehow I'm like souping up the topology, right? I'm looking in a stronger topology. Of course, then that makes the lower bound harder to prove. Right? Yeah.
How would you, like, if you had to guess what the rate function is, what is like the intuitive explanation?
Yeah, so you can rewrite this rate function in a nicer way, but it's if you're just to guess, that's a good question.
I guess it came out of your proof, right? So that's
I mean, one thing you can do. So if you stop here, this term here, it's a martingale that vanishes as n goes to infinity. And what you can kind of do is if you imagine this this whole thing satisfied like Friedland-Wenzel, like the Friedland-Wenzel LDP, you could like use that to sort of justify this. Does that help? I mean,
yes.
Yeah. Does that help? That's one way to see it. I mean, yeah. Yeah. I mean, you can also rewrite the rate function in a way. You can write it as I over 4 sigma integral 0 to time, say in the non-interacting case. You can nu. You can write it like this squared. Oh, you can rewrite it in this way for some appropriate norm.
First couple characters. The T.
So time derivative of nu t. You can rewrite this. So this really says, this thing is, it looks something like a Friedland. It's an L2 distance of the divergence from this from the equation I should solve.
So it's like a Gaussian.
Yeah, exactly. Yeah, which you expect it might just Gaussian. Maybe. I mean, there's other
even in the LDP, I guess, because it's kind of not that large deviation.
I mean, another thing is there's a relationship here to tangent spaces of in like the Wasserstein geometry, but maybe that's too much to get to. Okay, I won't get to it. Okay, sorry.
Let's see the answer.
I mean, this, I didn't include it because it's harder in the proof. Right? Anyway, so you need to do this. Here's my result.
Can I ask,
Mhm.
this appearance of Fn is just like an artifact of proof, and you expect that this should be
True without Fn. So I'm going to prove it with Fn because it's way easier to prove it with. And yeah, it's just an artifact of this proof. And then I'm going to show how you actually can get rid of Fn. I mean, this is a stronger result in a way. I mean, okay, the upper bound is weaker, right? It's a stronger topology, but the lower bound is stronger. So it's not like clearly that wrong. And also, if it's natural to talk about the mean field convergence for these systems using the modulated energy, it makes sense to talk about deviations using the modulated energy too.
Is it
But
possible to turn this
into a full LDP? Or
like into a full LDP with a stronger topology, like replace?
so the thing is you're never going to be able to show exponential tightness in this topology of these systems. Like they just aren't going to be exponentially tight. So this local result, you're never going to be able to like soup it up to a
I see. But that's just because it's too
strong.
That's just it's too strong a
Yeah,
topology to have
yeah.
large.
Yeah, exactly. Yeah. I mean, somehow, the modulated energy, it's exactly matched to like the dynamics of the system. So your system only wants to like decrease this in a sense. Yeah. So, right, it's like, yeah. These systems are gradient, you're doing gradient descent of some interaction energy that looks kind of like a negative Sobolev energy that corresponds to the modulated energy. So, you're never going to expect to have exponential tightness in this space. Yeah. Answer your question? Okay. If this equals 0, you can also show that nu has to be the solution to the Minkowski-Vlasov equation. Okay. So how do you prove this? Well, we need this function to be continuous for fixed phi. When s equals 0 and d equals 1, if you just write this term out, you can actually see, so here we're in 1D, so the gradients become, just derivatives, primes. This function here actually has a continuous extension, right? As x goes to y, this thing should converge to the second derivative of phi, as long as phi is regular. So when you're in this regime, you can basically write this as a continuous bounded extension, and you can just proceed like normal in the normal topology, right? In the normal weak topology. You can't do this when s is greater than 0. This is just not true. In fact, this term can have a singularity at x equals y, like x minus y to the s. However, if you look at this term, it looks kind of like exactly the term that was being bounded by the commutator estimate that I wrote earlier.
What
And
is
in
S?
s,
Oh, is that S there?
what? Sorry,
Oh, I see. It's
the strength of the capital S.
GX.
Yeah.
But it's always negative for you, right? Oh no, it's
always
minus
positive.
S.
It's always positive. Yeah. It's always repulsive, right? It always has a singularity there.
Also, this is something that you can't do because you want to use these. You want S greater than 0.
Yeah, exactly. Yeah. What you can do is you can adapt the commutator estimate, and you can bound exactly, something that looks like that. You can bound this kernel here being integrated against an empirical measure minus some target measure, and you can bound it by something that depends on the modulated energy. It's just a modification of the previous step.
You're still trying to prove this large deviation principle with the f's less
Yeah.
than epsilon. Okay.
Yeah, this is the proof of that. I'm almost done, out of time, 5 minutes, okay. In particular, if the supremum of the modulated energy between some trajectories and a measured trajectory goes to 0, then this entire term has to go to 0. This difference. This is essentially just proving continuity of this new term that shows up in this S function. So since f and x tn also controls weak convergence, these other terms that didn't have a singularity, they also have to converge to nu. So you just find this. If this holds, then S mu n phi has to converge to S nu phi. Okay. And you just immediately recover this upper bound, essentially. Yeah. So I mean, this is kind of, again, all you're doing is like looking at a stronger topology, which makes your thing continuous. Okay. For the lower bound, I'm almost out of time, so I think I'll just skip this. All you have to show is you have to show sort of a uniform mean field limit with respect to the modulated energy, and the lower bound just goes through for free for perturbed systems. So you have to show if you have the system, you can show something like that, and really it just follows by an Ito formula argument with Gronwall's argument with a Dupes inequality. Okay, but you get those two things, and you get the theorem. Okay, I don't find this very satisfactory because as we discussed, you're never going to be able to make this a global bound. Right? You're never going to be able to get the full LDP. So it turns out if you introduce an auxiliary function that depends on some Sobolev norms that should be nu. So I'm sorry, that should be nu and a nu. You can basically modify the rate function and get almost a full LDP in the weak topology. So if you define I nu to be the old rate function plus something that depends on this auxiliary function, you can show that if the modulated energy of the initial conditions converges and goes to infinity for some measure, then I has compact sublevel sets. You get a full upper bound, and this is all in this topology on C, continuous functions to prob measures, and also you get almost a full lower bound. So you get lower bound, except you don't get every point in the lower bound. There's some dense set that you get the lower bound for. Yeah. Somehow this has to do with finishing the approximation argument to get arbitrary regular trajectories. Okay, I'm almost out of time. I'll just very quickly go through the last slides. What you use is the fact that these systems are undergoing gradient flow with respect to an energy. There's a natural energy that they want to decrease, and that means you can get natural energy bounds. In particular, you can show something like this: the supremum of some energy, this energy function, over time, you can give an exponential bound on it.
Sorry, these
Yeah.
Sobolev norms were adapted to this.
So there are
I mean,
quotation
the-
marks. They're quotation marks because
Yeah.
I'm excluding the diagonals, just like before. Yeah. So here, see this thing? It's almost a Sobolev norm, right?
Mhm.
But I have excluded the diagonal.
Okay,
So everything here is with quotation. Sorry, I just
okay, I just was
I'm-
trying to.
essentially just they're natural bounds you can use. And what you can do is you can use those bounds to interpolate between weak convergence and these bounds to actually imply the integral of the modulated energy goes to 0 as n goes to infinity. And that basically just allows you to show continuity, not just in this modulated energy distance, but also in the distance you want. Okay. I think I'm going to end it there. So it's not over. Yeah.
I have a question. So the lower bound only being on this band, is that,
Yeah.
sorry, do you think this is reality or technical?
I'm actually not sure. Yeah, I don't. I'm not sure. I mean, I definitely don't know how to prove better than it. I've thought about it a lot. I don't know. I mean, sometimes these are like these incomplete lower bounds are real, right? Like,
I never saw. I don't know.
yeah, I think sometimes they're real. I think, yeah. If all said you would, but yeah, I don't know. Yeah, it's a good question. Yeah.
So you said there's CLTs for these models, right?
Yes. Yeah.
Is it true that the large deviations is related to the CLT, like in the case of the Gaussians? So that the CLT would be like as if the large deviations were true near 0.
I mean, that's generally true. I haven't thought about it. How do you prove a CLT using this? I'm not sure. Yeah.
Especially because you had those L2 norms. Like that.
It's not a question of proving, it's a question of, is that the
Yeah, it's
answer?
just.
Oh, is there?
Whether it match, right?
Wait, sorry, I don't understand. Wait.
So could you like heuristically prove the CLT, which is already proven rigorously by saying, okay, well, the large deviation is roughly true for very small values as well.
Yeah, you should.
It's like the density is like e to the minus.
Yeah,
raised
for
to the
sure, for
minus.
sure, for sure.
That's always true in Benson.
Yeah, yeah, yeah,
That's true, yeah.
for sure. Yeah, for sure.
So you said your last result, it's like a local LDP, not a full.
So it's just a local LDP because I don't have a full lower bound. I mean, arguably, so like a local, really what a local, it's like you have the LDP, but not for everything.
And then
Right? There's a local bound. Yeah, yeah, it's a weaker topology. I get exponential tightness. Yeah. Also, I mean, I'm doing more like this class, when you introduce this auxiliary function, it reduces the class of measure trajectories you have to care about. So before I was only talking about like trajectories that were L infinity time, L infinity space, for which like these terms were obviously integrable with these singular terms, but this allows you to like talk about a much larger class of measure trajectories. Yeah, I mean, it's quite technical to actually get.
Instead, you just looked at like the random variable that's just like a linear statistic.
Yeah.
You got like a full LDP just for that random variable.
I don't think so, or I don't know how to do it. Yeah. Yeah.
But
No,
it's like
I don't.
it's not.
Yeah, but it's kind of like if you could get the LDP for every, I don't know, every linear observable, right? Shouldn't you? You should probably be able to prove it. You know, bullshit stuff.
Is it ever not true? Like, if you make the singularity just absolutely horrible, can you make it false?
I don't know. So I can only prove this up to S d minus 2.
But
Yeah.
here's the thing, I mean, you got a repulsive potential.
Yeah,
So
yeah.
everybody's being pushed away from the singularity.
Yeah.
So the worse the singularity, the better. It should
Yeah,
be.
I know, but this is the weird thing. I totally agree, but in these energy bounds I really use, that's not the case, because when you take Ito's formula, you get a gradient of this thing. It kills you. Yeah. So that's like part of the reason there's this transition between subcoulomb and coulomb and up.
It would just be nice to see some cool phenomenon that you're trying to avoid or something. I guess nobody knows.
Yeah, I agree. Yeah, for sure.
Do you also put this light up on your nothing count?
Wait, what? Oh, I have to, right?
Or is that true?
Yeah, they tell you when you take the money, right?
It's like-
No one does it, but
I guess you are.
they say it on the website. They say you have to put this up on when you give a, and they say you have to put it in French. I think you're supposed to read it too, which I'm not gonna do. But oh,
We send it all. So that's-
okay.
Maybe you want-
Maybe this part can get cut. Okay, are there any more questions? Thank you for coming.
So you're here for a few days, right?
Yeah, I'm here until the end of the week. So, yeah. Yeah.
By the way, can you do just a random matrix again, like it's just like distance running motion?
Can I?
Yeah.
Yeah.
It follows from.
Yeah. Somehow, actually, I can prove a full, oh, that's another thing. I can prove a full LDP for any log easily, basically. For S equals 0, I can prove the full LDP. Yeah. So it's like a totally different regime somehow than the stronger, yeah.
But with sigma being 1/√.
No, I actually, I think I can prove my local bounds with sigma being 1/√n too. The FN bounds, I think I can prove those.
But I guess Joey would already put this anyway. From like your first slide.
So they do it, yeah, I mean, it's already done for Dyson bounding motion. They actually, in that paper, they're doing LDPs for the singular values of like rectangular ensembles. Yeah, they somehow like, they look at the singular values as like a, it's a tilting of the normal